Hi, my name is Luc Keijsers and my PhD within the PrimaVera project is about hybrid prognostic methods. Here we combine physical knowledge with data-driven approaches to predict breakdowns of machinery or structures. Imagine you would like to go on your well-deserved holidays, but just when you want to leave your car breaks down. Isn't that inconvenient? By performing maintenance just before breakdowns, we can on the one hand prevent such an inconvenient scenario, but also fully utilize systems to their full potential until the end of their actual life. This saves both inconvenience and money. In the current industrial era, you can notice the enormous increase of data that is being collected and stored everywhere. Sensors in your smartwatch monitor your physical well-being. And so can sensors in your car be used to monitor the health state of your car. Data from historical breakdowns can be used to train machine learning algorithms to learn patterns, such that future failures can be detected and predicted earlier. However, to keep you and other road users safe, your car gains preventive maintenance every year, or based on the amount of kilometers you have driven. For this reason, the most critical parts do not experience many failures, which is good for you, but it complicates the development of predictive algorithms. Luckily, we can also understand the physical phenomena behind failures. Furthermore, there is often a clear link between the usage of a system and the rates at which it degrades. By monitoring both the usage and the degradation of a system, we can update physics of failure models using Bayesian filters such as Kalman filters and particle filters. Using these filters, we can estimate the remaining time we can keep using our systems, known as the remaining useful life. The obtained relation between system usage and degradation also provides insights in how we can change our usage to prolong the lifetime, enabling maintenance rescheduling to a more convenient moment. As input for these filters, we preferably monitor degradation directly, for example by measuring the length of a crack or the amount of material that has been removed. Unfortunately, in many cases we can only measure indirect effects of degradation, such as increased vibration levels or temperatures. To understand the language our systems speak, we are working on models that represent damaged components. From this, we can extract virtual measurements, such as we understand the relation between indirect condition measurements and the actual degradation severity. We use bond graphs models for this purpose, which are known for their inter-domain applicability and modularity, enabling reusability. In the end, the combination of physics-based system and degradation models with real-time data and data-driven diagnostic algorithms form a hybrid framework for better failure predictions, such that unexpected breakdowns will become history and you can just enjoy your holidays. If you are interested in more information about the PrimaVera project, please visit primaveraproject.com for publications, podcasts, videos and more. See you there!